There is an object behind the sun right now. We call this 3i-ATLAS. And tomorrow, October 29th, it reaches perihelion. For most comets, perihelion is just another point along their journey. The closest approach to the sun, a moment of peak brightness, peak activity, and then they fade back into the darkness of space. But 3i-ATLAS is not most comets. Now, as it disappears behind the sun for what scientists are calling a solar eclipse from Earth's perspective, a small but vocal group of researchers has raised an uncomfortable question. What if 3i-ATLAS isn't just passing through? What if it came here on purpose? And then there's the question that Harvard astrophysicist Avi Loeb has been asking since the object's discovery. The question that has sparked heated debate in scientific circles and captured public imagination worldwide. Is there any possibility, any chance at all, that 3i-ATLAS is not entirely natural? We're going to explore that question, not because we believe it's true, but because in science, the most important questions are often the ones that seem impossible to ask. Chapter 1. The ATLAS Network. The Asteroid Terrestrial Impact Last Alert System wasn't designed to find interstellar objects. It was built to save lives. 4 telescopes, 4 locations spread across the globe: Hawaii, Chile, South Africa. Each one scanning the night sky every night, looking for anything that moves. The mission is simple: detect asteroids that might pose a threat to Earth, and detect them early enough to do something about it. ATLAS has been extraordinarily successful at this mission. Since its inception, the network has discovered thousands of near-Earth objects. Most are small, most are harmless, but a precious few, would have been catastrophic if they'd gone undetected. The system works by taking repeated images of the same patch of sky and comparing them. Anything that changes position between images gets flagged. Software algorithms analyze the movement, calculate trajectories, and determine whether an object is worth investigating further. On the night of July 1st, 2025, the ATLAS telescope in Rio Hurtado, Chile, was doing exactly what it was designed to do: scanning, comparing, cataloging. And then it found something unusual. The object was moving. That was normal. Everything in space is moving. But this object was moving fast. Much faster than typical asteroids. Much faster than anything bound to our sun's gravitational field. The initial classification was simple: new asteroid, moving object, track and catalog. But when astronomers looked closer at the velocity data, something immediately stood out. This wasn't just fast. This was escape velocity fast. Let's establish some context here. The planet Earth orbits the Sun at approximately 30 kilometers per second. That's about 108,000 kilometers per hour, or roughly 67,000 miles per hour. We're moving incredibly fast through space, but we don't feel it because everything around us is moving at the same speed. Mercury, being much closer to the Sun, has to orbit even faster to avoid falling into the Sun's gravitational well. It travels at about 48 kilometers per second. The object detected by ATLAS was clocked at 58 kilometers per second, and it was doing this out near Jupiter's orbit, where gravitational speeds should be much, much slower. That's when astronomers knew they were looking at something special. When you trace the orbit of an object backward through time, you can determine where it came from. For most objects in our solar system, this calculation leads back to the Sunday. They've been orbiting our star for billions of years, following elliptical paths that bring them closer and farther away but never truly escape. But when astronomers traced 3i-ATLAS backward, the numbers told a different story. The orbit was hyperbolic, not elliptical. Hyperbolic orbits are open. They don't loop back. They're one-way tickets. This object had come from somewhere else. The designation was official on July 2nd, 2025. The 3i prefix was added to its name. Third interstellar object. The third confirmed visitor from beyond our solar system. Before we go further, let's talk about those other two. Chapter 2. The visitors before October 19th, 2017. A telescope in Hawaii spotted something odd. It was small, moving fast, and its trajectory was all wrong. When astronomers calculated its orbit, they found something unprecedented. This object had come from outside our solar system. It was the first confirmed interstellar visitor in human history. They named it Oumuamua, the Hawaiian word for scout. Oumuamua was strange from the beginning. Its shape was unusual, long and thin, like a cigar or perhaps a pancake, depending on which analysis you believed. It tumbled through space in an odd rotation, and most puzzling of all, it accelerated as it left the inner solar system, pushed by some force that astronomers couldn't immediately explain. Dr. Avi Loeb of Harvard University suggested that Oumuamua might be artificial. A solar sail, perhaps, or some kind of technological artifact. The idea was controversial. Most scientists argued that the acceleration could be explained by outgassing the release of trapped gases as the object warmed near the sun, acting like tiny rocket thrusters. But the debate sparked something important. It made scientists realize that interstellar objects could look very different from what we're used to seeing in our own solar system. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar visitor using a telescope he built himself. This one was different. 3i Borisov looked like a comet. It acted like a comet. It had a visible coma, a cloud of gas and dust surrounding its nucleus, and a tail streaming behind it. Spectroscopic analysis showed water vapor, carbon monoxide, and other compounds you'd expect from a typical solar system comet. Borisov was, in many ways, reassuringly normal. It suggested that comets throughout the galaxy probably look similar to our own. Same basic composition, same basic physics. And then, 6 years after Oumuamua and 6 years after Borisov, came 3i-ATLAS. It's helpful to compare all three objects side by side. Oumuamua was small, maybe 400 meters across at its longest point. Probably a fragment of something larger, tumbling through interstellar space for who knows how long. It showed no obvious cometary activity, no coma, no tail, just a dark, reflective surface that rotated every 7.3 hours. 3i Borisov was larger, about 1 kilometer in diameter. Very clearly a comet, with a bright coma visible even from Earth-based telescopes. It moved at about 32 kilometers per second relative to the Sun, carrying the chemical signature of carbon monoxide. 3i-ATLAS is much larger. Initial estimates placed its diameter at 5.6 kilometers, though more recent analysis suggests it could be even bigger. Its speed, 58 kilometers per second, is nearly double that of the previous two visitors. But size and speed aren't the only differences. Oumuamua came from the direction of Vega, approaching from above the plane of the solar system at a steep angle. It was like someone had thrown a rock over a fence coming in from the north, passing through at an angle and leaving to the south. 3i Borisov approached at a less extreme but still significant angle, coming in from the direction of the constellation Cassiopeia. Again, well above the ecliptic plane. 3i-ATLAS is different. It's coming in nearly perfectly aligned with the ecliptic plane, the flat disk where all the major planets orbit. The angle is just 4.89 degrees off. For context, Pluto's orbit, which is considered quite tilted, is 17 degrees off the ecliptic. This alignment is statistically unusual. Space is three-dimensional. An interstellar object can approach from any direction. The probability of randomly arriving within 5 degrees of the ecliptic plane is less than 0.2%. Some scientists argue this isn't necessarily suspicious. The Milky Way galaxy has its own disk structure, and most stars orbit in that plane. Objects ejected from other star systems might naturally tend to follow paths roughly aligned with the galactic disk, which happens to be oriented similarly to our solar system's ecliptic. But it's still unusual, and combined with everything else we've observed about 3i-ATLAS, it adds to a growing list of peculiarities. There's another major difference worth noting: the direction of origin. Both Oumuamua and Borisov came from directions where the sun was moving toward them as it orbits the galactic center. We sort of ran into them as they drifted through space. 3i-ATLAS is coming from the side. A T-bone approach. From the direction of the galactic core, but perpendicular to our direction of motion. This trajectory brings it unusually close to several planets. On October 3rd, 2025, it passed within 29 million kilometers of Mars. In March 2026, if current projections hold, it will pass within 54 million kilometers of Jupiter. The probability of an interstellar object randomly passing this close to multiple planets on a single trajectory, less than 0.005%. Again, low probability doesn't mean impossible. Millions of interstellar objects probably pass through our solar system over millions of years. Some will inevitably have unusual paths purely by chance. But the numbers are worth noting, because when you start adding up all the unusual characteristics of 3i-ATLAS, the alignment, the trajectory, the close planetary encounters, the size, the speed, you start to see why some scientists are paying very close attention. Now let's talk about what the object is actually made of. Chapter 3. The chemistry problem. The first detailed observations of 3i-ATLAS came from the Hubble Space Telescope on July 21st, 2025. Hubble's images showed something astronomers expected to see: a bright, teardrop-shaped cocoon of dust surrounding the object's nucleus. This is normal for comets as they approach the sunday. The heat causes ice to sublimate, turning directly from solid to gas, and this gas carries dust particles off the surface, creating the familiar glowing cloud we call a coma. What wasn't normal was how early this coma appeared. When Hubble captured those images, 3i-ATLAS was still 364 million kilometers from the sunday. That's about 2.4 astronomical units well beyond Mars's orbit. At that distance, most solar system comets are still frozen solid. The sun's heat hasn't penetrated deep enough to cause significant sublimation. But 3i-ATLAS was already active, already outgassing, already producing a visible coma. This suggested the object was made of something more volatile than water ice, something that could sublimate at much lower temperatures. On August 6th, 2025, NASA's James Webb Space Telescope pointed its near-infrared spectrograph at 3i-ATLAS. Spectroscopy is one of the most powerful tools in astronomy. By analyzing the wavelengths of light coming from an object, we can determine what chemicals are present. Each element and compound absorbs and emits light at specific wavelengths, creating a unique signature. The Webb data revealed something unexpected. The coma of 3i-ATLAS was dominated by carbon dioxide, CO2 gas, not water vapor, not carbon monoxide, carbon dioxide, with a ratio of about 8:1 compared to water. This is essentially the opposite of what we see in typical solar system comets, where water ice is the primary component and CO2 is a minor constituent. The implication was clear. 3i-ATLAS formed in an extremely cold environment, colder than the outer regions of our own solar system. In conditions where carbon dioxide ice was more abundant than water ice. This makes sense for an interstellar object. Out in the depths of space, temperatures can drop to just a few degrees above absolute zero. Under those conditions, carbon dioxide would freeze readily, potentially dominating the composition of any comet that formed. But the chemistry story gets stranger. In September 2025, astronomers using the Very Large Telescope in Chile detected something unusual in the light spectrum coming from 3i-ATLAS. Nickel vapor. Specifically, they detected nickel in the object's coma at a rate of about 4 grams per second. This might not sound like much, but it's significant. Metals don't typically sublimate from comets unless they're very close to the sun and very hot. More puzzling was what they didn't detect: iron. In every known comet, both from our solar system and from interstellar space, nickel and iron appear together. This makes sense because both metals form in the cores of dying stars and are typically found mixed together in cosmic dust. When a supernova explodes, it spreads these metals throughout space, and they get incorporated into new star systems as they form. The nickel-to-iron ratio in comets is usually close to 1:1. Sometimes it varies, but both metals are always present. In 3i-ATLAS, the ratio appeared to be heavily skewed toward nickel. The amount of iron was below detection limits. This sparked immediate discussion in the scientific community. What natural process could separate nickel from iron so completely? How could a comet form with this unusual metal composition? Some researchers suggested that the carbon dioxide in the coma might be reacting with nickel-bearing dust grains to form nickel carbonyl, a complex molecule where nickel atoms bond with carbon monoxide groups. This compound is volatile and could explain why nickel appears as a gas while iron remains solid. The interesting thing about nickel carbonyl is that on Earth, it's primarily known as an industrial chemical. It's used in metal refining processes. The Mond process, specifically, uses nickel carbonyl to purify nickel metal. Finding this compound in space isn't impossible. The conditions needed to form it, carbon monoxide, nickel, and moderate temperatures, can exist naturally. But it's unusual, and it adds another data point to the growing list of 3i-ATLAS's peculiarities. Then, in late September, something changed. Astronomers detected iron in the coma for the first time. The nickel-to-iron ratio quickly shifted towards something more normal. Whatever process had been suppressing iron emission apparently stopped, or conditions changed to allow both metals to sublimate together. This pattern of sudden changes would repeat several more times as 3i-ATLAS approached the Sunday. By late September, as the object passed through 1.5 astronomical units, it began releasing massive amounts of water vapor. The emission rate was described as equivalent to a fire hose running at full blast, far more than astronomers would expect from a comet at that distance. The water release was so sudden and so intense that it caught observers by surprise. Most comets gradually increase their activity as they approach the Sunday. The sublimation builds slowly, predictably. 3i-ATLAS seemed to turn on like a switch. This behavior suggested several possibilities. Perhaps the carbon dioxide ice near the surface had sublimated away, exposing underlying layers of water ice. Perhaps cracks or fissures in the nucleus suddenly opened, allowing trapped water to escape. Or perhaps the internal structure of the object was fundamentally different from solar system comets. That last possibility is worth considering. If 3i-ATLAS formed 7 to 10 billion years ago, as its trajectory suggests, it would have experienced countless cycles of cosmic radiation, temperature fluctuations, and possible collisions during its journey through interstellar space. Its internal structure might be layered, fractured, or heterogeneous in ways that typical solar system comets are not. One more chemical detail deserves attention: cyanide. Cyanogen, a compound of carbon and nitrogen, was detected in the coma of 3i-ATLAS in early August. This is not unusual for comets. Many contain organic compounds. But when you start adding up the chemical inventory: carbon dioxide, water vapor, nickel, cyanogen, carbon monoxide, you get a picture of an object that's chemically complex and potentially very old. These compounds tell a story. They suggest that 3i-ATLAS formed in a protoplanetary disk around another star, billions of years ago, in conditions very different from those in our own solar system's history. They suggest long storage in the cold of interstellar space, and they suggest recent activation as the object encounters heat it probably hasn't experienced in eons. But chemistry isn't the only unusual feature of 3i-ATLAS. Let's talk about its appearance. Chapter 4. The tail that points the wrong way. Comets are defined by their tails. That's how we recognize them. That's how we've known about them for thousands of years. A bright head, a long streaming tail, moving slowly across the night sky over weeks or months. The tail of a comet is created by solar wind and radiation pressure. As the comet approaches the sun, ice on its surface sublimates into gas. This gas, along with dust particles, streams away from the nucleus in all directions. But the solar wind, a constant stream of charged particles flowing outward from the sun, pushes this material preferentially in one direction, away from the sunday. This is why comet tails always point away from the sun, regardless of which direction the comet is traveling. A comet approaching the sun has its tail streaming behind it. A comet leaving the sun has its tail streaming in front of it, but in both cases, the tail points away from the star. This is fundamental comet physics. It's been observed and confirmed countless times. So when astronomers using the Keck 2 telescope in Hawaii captured images of 3i-ATLAS in August 2025, they were surprised to see something unusual. A jet of material pointing toward the sunday, not a tail, a jet, a narrow, focused stream of gas and dust, extending about 10,000 kilometers from the nucleus, aimed directly at the sunday. This feature, sometimes called an anti-tail, is not completely unheard of in comets, but it's rare, and the mechanism behind it is often misunderstood. True anti-tails typically form when a comet's orbital geometry creates an optical illusion. From certain viewing angles, parts of the comet's normal dust tail can appear to extend forward. It's a perspective effect, like how railroad tracks seem to converge in the distance, even though they're parallel. But the jet observed on 3i-ATLAS wasn't an illusion. The spectroscopic data confirmed it. Material was actually moving toward the sunday. There are a few natural explanations for this. One involves the rotation of the comet's nucleus. If the nucleus is spinning, and if a particular active region on its surface happens to be oriented toward the sun at the right moment, gas jets can spray in seemingly unusual directions. As the nucleus rotates, this jet would sweep through space like a lighthouse beam. Another explanation involves the size and velocity of dust particles. If the dust grains being ejected are unusually large and heavy, they might not respond immediately to solar radiation pressure. They'd continue moving in their initial direction for a while, before eventually being pushed back into the normal anti-solar direction. This could create a temporary forward-pointing structure. Both explanations are physically plausible. Neither requires anything beyond normal comet behavior. But the timing was interesting. The sunward jet was observed primarily in July and August 2025, when 3i-ATLAS was still relatively far from the sunday. By September, when other telescopes captured new images, the jet had transformed into a more conventional tail pointing away from the sunday. This transition is exactly what you'd expect if the jet was being caused by volatile ices sublimating on the sunward side of the nucleus. Early on, the solar wind isn't strong enough to immediately push the material back. But as the comet gets closer and the solar wind intensifies, the physics change. The gas and dust start flowing in the expected direction. There's another aspect of this phenomenon worth mentioning. Dr. Avi Loeb and colleagues published a paper in October suggesting that this directional change from a sunward jet to an anti-solar tail could be interpreted as evidence of controlled maneuvering. If one were to hypothesize that 3i-ATLAS was a spacecraft, the logic goes like this. If an alien spacecraft wanted to slow down as it approached the sun, it might fire a braking thruster. This thrust would point toward the sun, and the exhaust would appear as a jet in that direction. Then, after completing the braking maneuver, the spacecraft would shut off its engines. The jet would disappear, and any normal outgassing from the craft's surface would form a typical tail. It's a creative hypothesis, and from a purely theoretical standpoint, it's testable. If 3i-ATLAS's trajectory shows evidence of non-gravitational acceleration during the period when the sunward jet was visible, that would suggest something was pushing the object. If the acceleration stops when the jet disappears, that would be consistent with an engine shutting off. However, as of the most recent observations in September 2025, no non-gravitational acceleration has been detected. The object is moving exactly as it should under the influence of gravity alone. This strongly suggests that the sunward jet was a natural phenomenon, unusual, yes, but not requiring artificial propulsion to explain. There's one more detail about the tail worth discussing. It's something called polarization. When light bounces off particles, it becomes polarized. The direction of polarization tells us about the size, shape, and composition of those particles. Most comets show positive polarization in their reflected light, meaning the light waves align in certain predictable ways. 3i-ATLAS shows extreme negative polarization, the most negative polarization ever recorded for any comet. This tells us something about the dust in its coma. The particles are probably very small, very uniform in size, or made of materials with unusual optical properties, or perhaps all three. Again, there's no rule that says interstellar comets have to have the same dust properties as solar system comets. Different formation conditions could easily produce different particle distributions, but it's another data point, another oddity to add to the list. Now, let's talk about one of the most frustrating aspects of studying 3i-ATLAS, the timing of its closest approach to the Sunday. Chapter 5. The Eclipse, 25 to 30, 31 to 0, October 29th, 2025. Today, right now, as you're reading this, 3i-ATLAS is reaching perihelion, its closest approach to the Sunday, at approximately 1.36 astronomical units, or about 203 million kilometers. It's passing just inside the orbit of Mars. For astronomers, this is the most important moment of the object's entire passage through our solar system. This is when 3i-ATLAS will be at its brightest. This is when the sun's heat will be most intense, causing the maximum amount of sublimation. This is when we should be able to learn the most about its composition, structure, and behavior. But we can't see it. Not from Earth. Anyway, the geometry of the solar system right now places 3i-ATLAS directly on the opposite side of the sun from our planet. From our perspective, the object is hidden behind our star. The overwhelming brightness of the sun drowns out any possibility of direct observation. This isn't an accident of timing. It's not bad luck. It's simple orbital mechanics. 3i-ATLAS's trajectory brought it to perihelion at this specific date and time. And at this specific date and time, we happen to be on the wrong side of the sun to watch. For most comets, this wouldn't be particularly significant. We'd lose sight of the object for a week or two, then pick it up again on the other side. We'd miss the perihelion observation, but we'd still get plenty of data before and after. But 3i-ATLAS isn't most comets, and the timing of this eclipse has raised some interesting questions. In orbital mechanics, there's a technique called an Oberth maneuver. It's named after Hermann Oberth, one of the founding fathers of rocketry and spaceflight. The principle is simple. If you want to change your speed in space as efficiently as possible, you should fire your engines at the moment when you're moving fastest. This is usually at periapsis, the closest point to whatever body you're orbiting. The reason this works has to do with kinetic energy. When you're moving fast, any additional thrust produces a bigger change in kinetic energy than it would if you were moving slowly. It's like the difference between accelerating a car that's already going 60 miles per hour versus accelerating from a standstill. The same amount of force has a bigger effect when you're already in motion. Spacecraft use Oberth maneuvers all the time. They dive close to a planet, fire their engines at closest approach, and slingshot away at much higher speeds than would otherwise be possible. Now consider the reverse scenario. Imagine an interstellar spacecraft approaching our solar system at high speed. If it wants to slow down to brake and enter orbit around the sun rather than just flying past, the most efficient place to do that is at perihelion. Fire the engines when moving fastest relative to the sun, and you get maximum deceleration for minimum fuel. This would be called a reverse Oberth maneuver. Here's where things get interesting. If an intelligent civilization wanted to send a probe to our solar system, and if they wanted that probe to enter orbit rather than just making a flyby, the optimal strategy would be to time the arrival so that the braking burn happens at perihelion. And if they were clever, if they wanted to avoid detection during this critical maneuver, they might time it so that perihelion occurs when the probe is on the opposite side of the sun from the civilization they're approaching. In other words, exactly the geometry we're seeing right now with 3i-ATLAS. To be absolutely clear, there is no evidence that 3i-ATLAS is performing any kind of maneuver. The object's trajectory remains consistent with pure gravitational motion. If it were firing engines right now, we would expect to see changes in its orbital parameters when we pick it up again in November. But the geometry is nonetheless striking, and it's one of several factors that have led some researchers, most notably Dr. Avi Loeb, to suggest that we should take seriously the possibility, however remote, that 3i-ATLAS might be artificial. Let's examine that argument carefully. Loeb and colleagues published a paper in October 2025 titled, "Is the Interstellar Object 3i-ATLAS Alien Technology?" The paper explicitly frames itself as a pedagogical exercise, a thought experiment designed to explore what an artificial interstellar object might look like and how we would detect it. The authors list several characteristics of 3i-ATLAS that they argue are consistent with, though not proof of, technological origin. 1. The trajectory's alignment with the ecliptic plane, 4.89 degrees off, compared to random expectation of to 45 degrees average. 2. The close approaches to Venus, Mars, and Jupiter probability is less than 0.005% for random arrival time. 3. The perihelion eclipse from Earth's view, optimal for clandestine maneuvering. 4. The unusual chemical composition, nickel without iron. 5. The sunward jet, potentially consistent with thrust. 6. The extreme negative polarization, unusual optical properties. 7. The size much larger than previous interstellar objects. Each of these points, taken individually, has natural explanations. But the paper argues that the combination of all 7 factors is statistically unlikely and worthy of serious investigation. The paper's conclusion is carefully worded. Given the dramatic implications, we can apply the logic of Pascal's wager that suggested it is more rational to believe in God's existence than not. In other words, even if the probability of artificial origin is very low, the consequences, if true, would be so significant that we should investigate thoroughly. The cost of investigation is minimal. The cost of ignoring a genuine artificial object would be enormous. It's worth noting that the vast majority of astronomers disagree with Loeb's assessment. Tom Statler, NASA's lead scientist for solar system small bodies, stated, "It looks like a comet. It does comet things. It very, very strongly resembles, in just about every way, the comets that we know." Dr. Michael Kuppers of the European Space Agency has been even more direct. 3i-ATLAS is behaving like a normal comet from another star. Nothing in its motion or makeup compels an exotic explanation. These are the mainstream scientific views. They represent the consensus position, and they're based on solid evidence and reasonable interpretation of the data. But Loeb's argument raises a deeper question about how science should approach truly unusual phenomena. If an artificial interstellar probe did enter our solar system, what would it look like? How would we recognize it? What tests would we perform to distinguish it from a natural object? These are legitimate scientific questions, and the Loeb paper, whatever its other merits or flaws, has forced the astronomical community to think carefully about them. Meanwhile, 3i-ATLAS continues its journey, hidden from view, approaching the Sun at a distance where, if it were artificial, it could theoretically execute the most efficient braking maneuver possible. In about 8 days, it will emerge from behind the Sunday ground. Base telescopes will be able to observe it again. We'll get new spectroscopic data, new images, new measurements of its trajectory, and we'll learn whether anything changed during those 8 invisible days. Chapter 6. The Mars Flyby, 31-0, 36-30. On October 3rd, 2025, 3i-ATLAS passed within 29 million kilometers of Mars. This was the closest the object would come to any planet during its passage through our solar system. And unlike the perihelion event happening right now, this flyby was fully visible not to us on Earth, but to an array of spacecraft currently in orbit around and on the surface of the red planet. Multiple missions had been tracking 3i-ATLAS for weeks. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter were both positioned to observe. NASA's Mars Reconnaissance Orbiter, with its powerful high-rise camera, had the object in its sights. Even the Perseverance rover on Mars's surface pointed its cameras skyward, hoping to catch a glimpse of the interstellar visitor. The images started appearing on October 7, 2025. The European Space Agency released the first data from ExoMars TGO. The images showed 3i-ATLAS as a small, bright dot moving against the background of stars. The object's coma was visible, a fuzzy halo of gas and dust surrounding the nucleus. The exposures were challenging. The comet was faint, about 10,000 to 100,000 times dimmer than Mars's surface, which is what these cameras were designed to photograph. But they captured it. A genuine interstellar object photographed from Mars orbit. The closest images ever taken of such an object by human-made instruments. The Mars Express images came next. Similar results. A bright fuzzy blob moving perceptibly between sequential frames. Nothing spectacular, but scientifically valuable. The brightness measurements would help constrain the size and reflectivity of the nucleus. The color data would provide clues about surface composition. Then came the wait for NASA's images. The Mars Reconnaissance Orbiter's high-rise camera is one of the most powerful telescopes ever sent to another planet. It can resolve objects on Mars's surface down to about 30 centimeters. Pointed at 3i-ATLAS, even from 29 million kilometers away, it should have captured the clearest, highest resolution images of the object yet obtained. But as of October 27, 2025, those images have not been publicly released. The reason is prosaic and frustrating. The U.S. government shutdown that began in late September has left NASA operating with minimal staff. Many scientists have been furloughed. Communications teams are offline. Data processing pipelines are running, but public releases have been delayed. This has led to predictable conspiracy theories. Social media is filled with claims that NASA is hiding evidence, that the high-rise images show something unusual structures, emissions, geometric patterns that would force us to reconsider 3i-ATLAS's nature, that the shutdown is convenient cover for suppressing information the public deserves to see. The reality is almost certainly more mundane. The U.S. government shuts down periodically when Congress fails to pass funding legislation. When this happens, federal agencies cease non-essential operations. Public communications are considered non-essential. Data analysis continues, but press releases don't. Dr. Loeb has been vocal about his frustration with the delay. "Who cares about the communication departments?" he wrote in a recent blog post. "We want to see the data from the scientists." He has a point. The high-rise images exist. They were taken. They're sitting on servers somewhere, processed or being processed. The scientific value doesn't change whether they're released today or next month. But the public interest is intense, and delays feed speculation. Meanwhile, we do have images from the Perseverance rover. On October 4th, the rover's Mastcam Z instrument captured 2 exposures of the night sky above Jezero crater. Amateur astronomers analyzing the raw data files noticed something in the frames, a faint streak of light positioned roughly where 3i-ATLAS should have been. The streak is subtle. You have to stack multiple images and enhance the brightness to see it clearly. But it's there. A photographer named Simeon Schmaus was among the first to spot it, posting his processed images to social media with the caption, "I think Perseverance may have spotted interstellar comet 3i-ATLAS last night from Mars. The position matches, the timing matches, the brightness is consistent with predictions. It's almost certainly 3i-ATLAS, as seen from the surface of Mars, the first confirmed ground-level observation of an interstellar object from another world." These Mars observations are valuable for several reasons beyond their intrinsic coolness. First, they provide parallax measurements. By observing the same object from multiple locations millions of kilometers apart, we can triangulate its position with extreme precision. This helps refine our models of its trajectory and timing. Second, they give us a different viewing angle. From Earth, we see 3i-ATLAS edge on relative to its coma. From Mars, during the flyby, the viewing geometry was different. This might reveal structures or asymmetries in the coma that aren't visible from our perspective. Third, they demonstrate that 3i-ATLAS didn't change its behavior when approaching Mars. Some of the more speculative theories about artificial origin suggested the object might alter course to avoid planetary environments or perform close approach maneuvers near Mars. No such behavior was observed. The trajectory remained perfectly consistent with gravitational motion. But there's one more aspect of the Mars encounter that deserves attention. It has to do with what might happen in the coming months. Two spacecraft currently traveling through the inner solar system, the European Space Agency's Hera mission and NASA's Europa Clipper, are on trajectories that, according to recent calculations, will carry them through 3i-ATLAS's tail, not the visible dust tail. The ion tail. Comets actually have two tails, though we usually only see one with our eyes. The dust tail is the bright, visible one made of particles that reflect sunlight. But there's also an ion tail, made of electrically charged gas molecules that are invisible to optical telescopes but detectable by particle sensors. The ion tail can stretch for millions of kilometers. And because it's made of lightweight charged particles, it gets swept along by the solar wind in a nearly perfect radial line away from the sunday. Based on current models of 3i-ATLAS's outgassing rate and the solar wind conditions, researchers predict that Hera and Europa Clipper will pass through the outer reaches of the comet's ion tail sometime between late October and early November 2025. Neither spacecraft is designed for comet observation. Hera is headed to study a near-Earth asteroid. Europa Clipper is journeying to Jupiter's moon, Europa. But both carry plasma instruments and particle detectors for studying the space environment. If they pass through the tail, those instruments will detect it. They'll measure the composition, density, and velocity of the ionized gas. This would provide direct samples of material from an interstellar object, not just light reflected off its surface, but actual atoms and molecules from its interior, exposed by sublimation and carried away by the solar wind. The data won't be available immediately. Both spacecraft are far from Earth, and data transmission rates are slow. Europa Clipper's measurements might not be downlinked until early 2026, but when they arrive, they could provide some of the most detailed chemical analysis of interstellar material ever obtained. Now, let's talk about what happens next. Chapter 7, The Reappearance, November 7th, 2025. That's the date when 3i-ATLAS is expected to emerge from behind the Sun and become visible again to Earth-based telescopes. After 8 days of solar eclipse, during which the object will have passed through perihelion, completely hidden from our view, we'll finally be able to see it again. But by then, it will have changed. Perihelion is a transformative event for any comet. The intense solar radiation heats the nucleus to temperatures it may not have experienced in billions of years. Ice that has been stable for eons suddenly sublimates. Trapped gases burst out, dust layers peel away. The object sheds mass, alters its surface, potentially fragments into pieces. For 3i-ATLAS, this transformation is happening right now, in real time, about 203 million kilometers away, and we can't watch it. When it reappears, on November 7th, astronomers expect to see changes. The coma should be larger and brighter. The tail should be more prominent, possibly stretching millions of kilometers. The outgassing rate should have increased significantly. But there are other changes that might be more subtle and more important. If 3i-ATLAS performed any kind of maneuver during perihelion, we'll see evidence in its trajectory. The orbital elements, the mathematical parameters that describe its path through space, will have shifted, not by much perhaps, but measurably. Ground-based observatories around the world are preparing for an intensive observation campaign when the object becomes visible again. The International Asteroid Warning Network has coordinated efforts to track it precisely. Not because it poses any danger, it doesn't, but because it represents a rare opportunity to study an interstellar object during its most active phase. The campaign will focus on several key measurements: astrometry, precise position measurements over time, allowing calculation of the exact trajectory; Any deviation from pure gravitational motion would indicate non-gravitational forces acting on the object, either natural outgassing or something else. Photometry. Brightness measurements over time, looking for variations that might indicate rotation, outbursts, or fragmentation. Spectroscopy. Chemical composition of the coma, tracking how it changes as the object moves away from the sun and different layers of the nucleus are exposed. Polarimetry. The polarization of reflected light, providing information about the size and nature of dust particles in the coma. Radar. If the object comes within range of Earth's powerful planetary radar systems, which it won't, unfortunately, we could measure its size, shape, and rotation directly. But at 1.8 AU minimum distance, it's too far for useful radar observations. The European Space Agency's Jupiter Icy Moons Explorer JUICE will observe 3i-ATLAS between November 2nd and 25th. JUICE is currently on its way to Jupiter, but it's positioned to get a good view of the comet post-perihelion from a different angle than Earth. JUICE carries multiple instruments that can contribute. Janus, a visible light camera that can image the coma structure wreck. Magis, an infrared spectrometer that can detect and map different ices and minerals place. SWI, a sub-millimeter wave instrument that can detect gas molecules, several particle detectors that might catch stray molecules from the tail's cis. The data from JUICE won't be downlinked until February 2026, due to the spacecraft's communication constraints. But when it arrives, it will provide a three-dimensional picture of 3i-ATLAS, combining observations from Earth, Mars, Jupiter's vicinity, and possibly the Europa Clipper in between. In March 2026, there's one more close encounter scheduled. 3i-ATLAS will pass within 54 million kilometers of Jupiter. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, will turn its instruments toward the comet. Juno wasn't designed for comet observation any more than Mars Express was, but it carries JunoCam, a color camera, gyrum, an infrared spectrometer, UVS, an ultraviolet spectrograph, MWR, a microwave radiometer. These instruments can provide additional data on the comet's composition and activity, particularly in wavelengths that are difficult to observe from Earth due to atmospheric absorption. By March 2026, 3i-ATLAS will be cooling down, moving away from the sun, heading back out into the cold of interstellar space. Its activity level will be decreasing. The coma will be shrinking, the tail will be fading, but it will still be visible, and it will still be worth studying, because even as it leaves, 3i-ATLAS will be teaching us about the galaxy. Every measurement we make, every spectrum we capture, every image we process adds to our understanding of what's out there, beyond our solar system, beyond our sun's influence. In the vast spaces between stars, where comets drift for billions of years, carrying within them the chemical and physical history of other worlds, we've learned that interstellar comets can be wildly different from each other. Oumuamua was dry and rocky. Borisov was wet and carbon monoxide rich. 3i-ATLAS is carbon dioxide dominated with unusual metal emissions. This diversity tells us something important. Planetary systems throughout the galaxy don't all form the same way. Different stars, different distances from their stars, different initial chemical abundances, all of these factors produce different kinds of comets. And when these comets are ejected from their home systems through gravitational interactions with giant planets, or close stellar encounters, or any number of other mechanisms, they carry that diversity with them into interstellar space. We live in a galaxy filled with these wanderers, objects ejected from countless star systems over billions of years. Most drift in the darkness between stars forever, but occasionally, by pure chance, one of them passes through another system. And when one passes through our system, we get a glimpse of another world, another time, another place in the galaxy's history. That's what 3i-ATLAS represents. A messenger from somewhere else, a time capsule from conditions we can only infer. a rare opportunity to study material that formed under circumstances that may never have existed in our own solar system. Even if every strange characteristic of 3i-ATLAS turns out to have a natural explanation and the overwhelming evidence suggests they will, the object remains extraordinary. Now, let's address the question everyone wants answered. Chapter 8. The Artificial Hypothesis. Let's talk about aliens. Not because there's strong evidence that 3i-ATLAS is artificial. There isn't. But because the question has been asked, publicly and repeatedly, by serious scientists. And because understanding why the question is being asked, and why most scientists reject the hypothesis, tells us something important about how science works. The artificial hypothesis, as articulated most fully by Dr. Avi Loeb and colleagues, rests on a foundation of low probability coincidences. Take the ecliptic alignment. The probability that an interstellar object would randomly arrive within 5 degrees of the ecliptic plane is about 0.2%. That's unusual, but not impossible. Over thousands of interstellar visitors spread across millions of years, you'd expect some to arrive at unusual angles. Now add the close planetary approaches. The probability that a given trajectory would bring an object within 30 million km of Mars and 54 million km of Jupiter is about 0.005%. Again unusual, again not impossible. Add the perihelion eclipse from Earth's perspective. This geometry isn't inherently rare. About 50% of solar system comets reach perihelion when Earth is on the opposite side of the Sunday. But combined with the other factors, it starts to look like a pattern. Add the unusual chemistry. Nickel without iron. Extreme negative polarization. Carbon dioxide dominance. Each of these has potential natural explanations, but each is unusual compared to known comets. Add the size. At 5 to 6 kilometers diameter, possibly larger, 3i-ATLAS is much bigger than the previous interstellar objects we've detected. If interstellar objects follow the same size distribution as asteroids and comets in our own solar system, they probably do. We should have detected hundreds or thousands of smaller objects before finding one this large. The artificial hypothesis looks at this list and says, the probability that all of these factors would occur together in a natural object is extremely low. Low enough that we should seriously consider alternative explanations. The hypothesis doesn't claim certainty. It doesn't say this must be artificial. It says the natural explanation is improbable enough that we should investigate the artificial possibility carefully, because the consequences, if true, would be significant. This is actually a reasonable scientific position, despite how it's been characterized in some media coverage. Science works by considering multiple hypotheses and testing them against evidence. When you encounter an unusual phenomenon, you don't just grab the first explanation that seems plausible. You list multiple possibilities, rank them by probability, and then gather more data to rule out alternatives. The problem comes when you start assigning probabilities to hypotheses without good prior information. What's the baseline probability that an interstellar object is artificial? We don't know. We have no data. We've never detected an artificial interstellar object. We've never detected any extraterrestrial technology. We don't know how common technological civilizations are in the galaxy. We don't know whether such civilizations build interstellar probes. We don't know what percentage of interstellar objects should be artificial versus natural. Without this information, we can't calculate a meaningful probability. Loeb has suggested a figure of 30–40% likelihood that 3i-ATLAS is not fully natural. But this number is based on subjective assessment of the anomalies, not on rigorous probability calculation. Other scientists would put the probability much lower, perhaps 0.01%, perhaps 0.00001%, perhaps effectively zero. The numbers don't really matter. What matters is the methodology. Here's what the scientific community generally agrees on. Agreement 1. 3i-ATLAS displays several unusual characteristics that make it interesting and worthy of detailed study. Agreement 2. Each unusual characteristic can potentially be explained by natural processes, though some explanations require conditions we haven't observed in other comets. Agreement 3. The combination of unusual characteristics is statistically uncommon but not impossible. Agreement 4. No direct evidence of artificial origin has been detected. No radio signals, no obvious structures, no unexplained acceleration, no maneuvers. Where scientists disagree is on what we should do with this information. The mainstream view, represented by NASA and ESA officials, is that we should proceed with the natural hypothesis until and unless evidence forces us to reconsider. This is the standard scientific approach. Prefer simpler explanations over complex ones. Don't invoke exotic possibilities when mundane ones suffice. Loeb's view is that when dealing with potentially high-consequence phenomena, we should be more proactive. Even if the probability of artificial origin is very low, the importance of detecting such an object would be so high that we should investigate thoroughly. In his words, we should keep our eyes open and not assume anything. This philosophical difference is actually healthy for science. It represents a creative tension between conservatism, which prevents us from chasing every wild idea, and openness, which prevents us from missing genuinely revolutionary discoveries. The history of science includes examples of both eras. Sometimes, the mainstream consensus rejects ideas that later turn out to be correct, continental drift, for instance, or the bacterial cause of ulcers. Other times, fringe ideas get too much attention before being definitively ruled out: cold fusion, the EM drive, faster than light neutrinos. So, where does 3i-ATLAS fall? Is this continental drift or cold fusion? The evidence, as it currently stands, strongly suggests it's a natural object. Here's why. Observation 1. The trajectory shows no signs of non-gravitational acceleration. If 3i-ATLAS were under power, if it were actively maneuvering, we would expect to see deviations from a purely gravitational orbit. These haven't been detected. Thousands of position measurements from May through September 2025 show residuals consistent with gravitational motion only. This is perhaps the single strongest piece of evidence against artificial origin. A spacecraft that travels for billions of years through interstellar space and then arrives at our solar system would need to make course corrections. Interstellar space isn't perfectly empty. There are gas molecules, dust grains, cosmic rays. Over such vast distances, these tiny perturbations would add up. Any spacecraft would need to adjust its trajectory periodically. If 3i-ATLAS were a spacecraft, and if it were planning to do anything other than fly straight through our system, we should have seen evidence of maneuvering by now. Observation 2. The spectroscopic signatures are consistent with a comet. Carbon dioxide, water vapor, carbon monoxide, cyanogen, carbonyl sulfide, all of these have been detected in known natural comets. The ratios are unusual, yes, but they fall within the range of what's chemically possible in cometary ices formed under different conditions than our own solar system. Observation 3. The object is losing mass through outgassing. Loeb's own calculations suggest 3i-ATLAS has shed about 2 million tons of material between July and October 2025. This is consistent with cometary sublimation. A technological artifact would presumably have more efficient ways of managing heat than venting billions of tons of gas into space. Observation 4. The behavior has been predictable. The changes we've observed, the shift from sunward jet to antisolar tail, the increase in water vapor emission, the metal detection patterns all follow sequences that make sense for a comet warming as it approaches the sunday. There have been no sudden, unpredictable changes that would suggest active control. Observation 5. The close planetary approaches, while statistically unusual, aren't unprecedented. Even in our own solar system, comets occasionally make close passes by multiple planets. The geometry that allows this happens to align with the plane where most matter in the galaxy resides, the galactic disk. An object ejected from a star system in the galactic disk would naturally tend to travel roughly within that plane. These observations don't prove 3i-ATLAS is natural. Proof is rarely possible in science. but they make the natural hypothesis much more probable than the artificial one. Still, Loeb has a point about the importance of investigation. If we're wrong, if 3i-ATLAS is artificial, and we dismiss it without proper study, we'll have missed the most important discovery in human history. So, what would proper study look like? Chapter 9. How to tell the difference. If an artificial interstellar probe did enter our solar system, how would we know? This is not a hypothetical question. With improved telescopes coming online in the next few years, particularly the Vera C. Rubin Observatory, which will scan the entire visible sky every few nights, we're going to detect many more interstellar objects. Dozens per year, eventually. Maybe hundreds. Most will be natural. Comets and asteroids ejected from other star systems, drifting through the galaxy. But if even 1 in a million is artificial, we need to know how to recognize it. Loeb has proposed several criteria. Think of them as a menu of tests we could apply. Test 1. Radio emissions. This is the most obvious one. Artificial objects might emit radio signals, either as communication or as waste heat from electronics or power systems. SETI researchers have been pointing radio telescopes at 3i-ATLAS for months, looking for any unusual signals at frequencies that wouldn't be produced naturally. So far, nothing. No signals detected. If 3i-ATLAS is artificial, it's either inactive, deliberately quiet, or communicating at wavelengths or in ways we're not monitoring. Test 2. Trajectory anomalies. Natural objects move according to gravity and, sometimes, outgassing forces. Artificial objects can maneuver. They can change course, adjust speed, orient themselves deliberately. As mentioned, no trajectory anomalies have been detected in 3i-ATLAS, but there's a caveat. Small course corrections might be below our detection threshold, especially if they occurred early in the object's approach when we had fewer observations. The real test will come in November and December, when we can observe the object again. If its post-perihelion trajectory differs significantly from predictions, that would be interesting. Very interesting. Test 3. Surface features. Natural objects should look natural. Irregular shapes, rough surfaces, random patterns of light and dark. Artificial objects might show geometric regularity, right angles, symmetries, patterns that don't occur in nature. We don't have high enough resolution images to check this for 3i-ATLAS. The high-rise images from Mars might help if they're ever released. But even high-rise, from 29 million kilometers away, won't show surface details smaller than several kilometers across. Test 4. Thermal signature. Active electronics generate heat. Even a dormant spacecraft might have residual thermal emissions from radioactive decay in its power systems. These would show up in infrared observations as temperatures slightly higher than expected from solar heating alone. NASA's James Webb Space Telescope observed 3i-ATLAS in infrared. The thermal signature was consistent with solar heating. No excess detected, but again, this doesn't rule out a dormant or very efficient artificial object. Test 5. Composition. Natural objects should have compositions that make sense for their formation environment. Ices that can condense at certain temperatures. Minerals that form in protoplanetary disks. Ratios of elements that match stellar abundances. Artificial objects might contain unusual isotopic ratios from nuclear processes, refined metals, purified beyond what occurs naturally, or compounds that require industrial production. The nickel without iron observation in 3i-ATLAS initially seemed suspicious in this category, but as iron was later detected, and as potential natural mechanisms for nickel carbonyl formation were identified, this anomaly became less compelling. Test 6. Behavior. Natural objects follow predictable patterns. Comets brighten as they approach the sun, following a mathematical curve related to sublimation rates. Asteroids rotate at rates determined by their formation history and subsequent collisions. Artificial objects might show unpredictable changes, sudden brightness variations, attitude adjustments, emissions that don't correlate with solar distance. 3i-ATLAS has shown some unusual behaviors. The sudden water increase, the direction change of the jet, but all can be explained by inhomogeneous composition and complex sublimation physics. Test 7. Longevity. This is a longer-term test. Natural comets break apart. They fragment under thermal stress, shed material, sometimes disintegrate completely near the sunday. If an object survives multiple solar passes intact or shows unusual structural stability, that might indicate artificial construction. We'll know more about 3i-ATLAS's structural integrity after perihelion. If it fragments, that's a strong sign of natural origin. If it emerges completely intact despite the thermal stress, that's less definitive, but interesting. Test 8. Response to communication. This is the boldest test, and the one most likely to seem silly. But if you seriously consider the artificial hypothesis, it follows that you might try to communicate. Some researchers have suggested beaming radar or laser signals at 3i-ATLAS to see if it responds. The signals would be deliberately structured sequences of prime numbers, mathematical constants, simple pictographs, anything to distinguish them from natural electromagnetic noise. No one has actually done this yet, as far as we know. The experiment would be expensive and unlikely to succeed, but it's theoretically possible. None of these tests, applied individually, can definitively prove artificial origin. Even if 3i-ATLAS responded to communication, there's always the possibility of false positives, natural phenomena that mimic signals, or human error in interpretation. But a combination of positive results across multiple tests would be compelling. An object that showed trajectory anomalies and radio emissions and geometric surface features and unusual thermal signature would be very difficult to explain naturally. 3i-ATLAS passes none of these tests. Or more precisely, it passes all of them in the sense that it looks natural on every metric where we have data. The artificial hypothesis remains possible only because of the absence of data in some areas and the statistical improbability of certain combinations. But absence of evidence for natural origin is not the same as evidence for artificial origin. This is where the scientific method becomes crucial. The burden of proof lies with extraordinary claims. The claim that 3i-ATLAS is artificial is extraordinary. Therefore, it requires extraordinary evidence. That evidence hasn't materialized, and every new observation has moved the needle further toward natural comet and away from artificial probe. But the question itself was worth asking, because someday, maybe with 3i-ATLAS, maybe with object number 47, maybe with object number 2394, we might encounter an interstellar visitor that doesn't have natural explanations. And when that day comes, we'll need to know what to look for. Now, let's talk about what all of this means for humanity's place in the universe. Chapter 10. The Bigger Picture. 3i-ATLAS is teaching us something profound about our galaxy, whether it's natural or artificial. It's teaching us that interstellar objects are diverse. 3 confirmed visitors. 3 completely different profiles. Oumuamua, small and enigmatic, with an unusual shape and unexplained acceleration. Borisov, medium-sized and cometary, looking almost exactly like what we'd expect from our own Oort cloud. 3i-ATLAS, large and active, with chemistry that points to formation conditions very different from our solar system. From just these 3 data points, we can infer that the galaxy is filled with tremendous variety. Different star systems produce different kinds of planets, asteroids, and comets. Different formation conditions lead to different compositions. Different ejection mechanisms lead to different trajectories. This has implications for our understanding of planet formation throughout the galaxy. When astronomers study exoplanets, planets orbiting other stars, they're limited to indirect methods. They can measure a planet's size, mass, and orbital period. With the best instruments, they can detect some atmospheric compounds, but they can't directly sample the materials that these planets are made of. Interstellar objects provide that direct sampling. Every one that passes through our solar system is carrying material from another star's planetary system, ice from a protoplanetary disk, minerals from a shattered planetesimal, organic compounds from billions of years of cosmic chemistry. By studying these visitors, we're essentially conducting interstellar reconnaissance without leaving our solar system. We're learning that water, the fundamental ingredient for life as we know it, is common throughout the galaxy. 2i Borisov had water. 3i-ATLAS has water. Both objects formed around other stars, far from our sun's influence. The fact that they contain water means that the conditions for life might be more widespread than we thought. We're also learning that planetary systems can be very old. The trajectory of 3i-ATLAS suggests it may have been ejected from its home system 7 to 10 billion years ago. That's more than twice the age of Earth. It's wandered through the galaxy since before our planet existed, carrying within it chemical information about conditions in the early Milky Way. This is humbling. We tend to think of our solar system as typical, average, a representative sample of what planetary systems are like. But every interstellar object we study shows us ways in which we're different. Our comets have more water and less carbon dioxide than 3i-ATLAS. Our inner planets are rocky, while some other systems might be dominated by icy super-Earths. Our Jupiter is in a certain orbit, but other systems have hot Jupiters or no giant planets at all. The more we look outward, the more we realize that normal is a local concept. What's normal in our neighborhood is unusual somewhere else. What's unusual here is commonplace there. This is actually good news for the search for life. If planetary systems are all similar, then life either evolves everywhere under the same conditions or nowhere because those conditions aren't sufficient. But if planetary systems are diverse, then life might arise through multiple different pathways, different chemistries, different energy sources, different evolutionary trajectories. The diversity we see in interstellar objects suggests that the galaxy is full of possibilities we haven't imagined yet. Let's think about the numbers for a moment. Our Milky Way galaxy contains somewhere between 100 and 400 billion stars. Most of them have planetary systems. That's tens or hundreds of billions of places where comets could form. Some fraction of those comets get ejected from their home systems through gravitational interactions. Current estimates suggest that each star system might eject trillions of small bodies over its lifetime. If even 1% of those escape the star's gravity completely and enter interstellar space, we're talking about an enormous population. Some calculations suggest there might be more interstellar objects than gravitationally bound objects in the galaxy. More comets and asteroids drifting between stars than orbiting within star systems. We're living in a galaxy that's absolutely filled with these wanderers, travelers from countless origins, moving in countless directions, following trajectories shaped by billions of years of gravitational interactions. And we've detected 3 of them, 3 out of trillions. The Vera C. Rubin Observatory, which is scheduled to begin full operations in early 2025, will change this dramatically. Rubin is designed to image the entire visible sky every few nights, looking for anything that moves or changes. It will detect asteroids, comets, supernovae, variable stars, anything transient, and it will detect interstellar objects. Current predictions suggest Rubin might find 1 interstellar object per month once it's fully operational. Maybe more. Within a decade, we could have a catalogue of hundreds of these visitors, each one offering a unique glimpse into another part of the galaxy. Some will be small, like Oumuamua. Some will be large, like 3i-ATLAS. Some will be icy, some rocky. Some will have unusual compositions that hint at formation conditions we've never considered. And maybe, just maybe, one of them will show characteristics that can't be explained naturally. This is why Loeb's artificial hypothesis, despite being unlikely for 3i-ATLAS specifically, is important for the future. We need to develop frameworks for recognizing artificial objects before we encounter one. We need to establish criteria, agree on tests, create protocols for investigation, because if an artificial interstellar probe does pass through our solar system, we have a limited time to study it. These objects move fast. They don't stay long. By the time the scientific community agrees on what to look for, the opportunity might have passed. 3. 3i-ATLAS, whether natural or artificial, is serving as a dress rehearsal. It's teaching us what to measure, what to look for, and how to coordinate international observations on short notice. The Mars flyby demonstrated that we can mobilize multiple spacecraft to observe an unexpected target. The spectroscopic campaigns showed that we can gather detailed chemical data quickly. The trajectory analysis proved that we can detect tiny deviations from gravitational motion if they exist. We're getting better at this, and we're going to need those skills because the interstellar objects are coming, more and more of them. As our detection capabilities improve, each one is a message in a bottle, a sample from another world, a chance to learn something we couldn't learn any other way. Even if 3i-ATLAS is just a chunk of ancient ice and rock, which it almost certainly is, it represents something extraordinary. It's a 7 billion-year-old time capsule from the thick disk of the Milky Way. It formed when the universe was younger. It's older than our sun, older than Earth, older than life on our planet. And for a few months in 2025, it passed through our cosmic neighborhood, close enough for us to study, before heading back out into the darkness of interstellar space. We should be grateful for the opportunity. Now let's address what happens next. Chapter 11. Perihelion and Beyond. Right now, at this moment, 3i-ATLAS is at its closest point to the Sunday. The temperature at its surface has reached levels it hasn't experienced in billions of years, possibly never. The ice is sublimating rapidly. Gas and dust are streaming away from the nucleus. The coma is expanding, the tail is growing, and we can't see any of it. This is frustrating for astronomers, but it's not catastrophic. We've learned an enormous amount about 3i-ATLAS already, from months of observation as it approached. We know its approximate size, its composition, its rotation, its outgassing patterns. What we don't know yet is how perihelion will change it. Some comets survive their closest solar approach intact. They lose mass, certainly. They might develop cracks or fractures, but their nucleus remains coherent, and they continue on their trajectory largely unchanged. Other comets break apart. The thermal stress creates fractures that propagate through the nucleus. Sections separate. What was one object becomes two, then three, then a scattered stream of fragments. Which will 3i-ATLAS be? The size suggests it should survive. Larger comets are generally more stable. They have more mass to hold them together, and their surface area to volume ratio is lower, meaning less thermal stress per unit of material. But 3i-ATLAS is also very old. It's been in cold storage for billions of years. That long duration in interstellar space, exposed to cosmic rays, bombarded by dust, undergoing countless freeze-thaw cycles as it passed various stars at different distances, might have weakened its structure. We'll find out on November 7th, when the object emerges from behind the sun and becomes visible again. The first priority will be position measurements. Where is it? Exactly. How fast is it moving? Has its trajectory changed? If the trajectory has changed significantly, that would indicate either fragmentation or non-gravitational forces. Fragmentation would cause the various pieces to spread out along slightly different orbits. Non-gravitational forces from outgassing or from something else would cause the whole object to deviate from its predicted path. The second priority will be imaging. How does it look? Is the coma larger? Is the tail more prominent? Can we see any structure or irregularity in the nucleus? The third priority will be spectroscopy. Has the chemical composition of the outgassing changed? Are we seeing material from deeper layers of the nucleus now that the surface has been stripped away? All of these observations will be done quickly, because 3i-ATLAS won't remain easily visible for long. As it moves away from the sun and from Earth, it will grow fainter. By December, it might require large professional telescopes to observe. By January 2026, it could be too faint for most facilities. The closest approach to Earth happens on December 19th, 2025. At that point, 3i-ATLAS will be approximately 1.8 astronomical units away, about 270 million kilometers. still far, much farther than Mars at its closest. But it's the best viewing opportunity we'll have from Earth-based telescopes. By then, the object will be cooling down, moving away from the Sunday. The sublimation rate will be decreasing, the coma will be shrinking, but it should still be active enough to study, and the geometry will be favorable for observation from the northern hemisphere. Amateur astronomers with decent telescopes, 8-inch apertures or larger, might be able to spot it as a faint fuzzy patch in the constellation Virgo. It won't be spectacular, no naked eye visibility, no long sweeping tail across the sky like some comets produce. Just a dim smudge moving slowly against the background stars. But for those who know what they're looking at, it will be extraordinary. An interstellar visitor, a traveler from another star system, something that has journeyed across light years and billions of years to appear in our sky for a few brief months. The professional observations will continue through December and into early 2026. Every spectrum captured, every brightness measurement recorded, every position noted adds to our understanding of this object and, by extension, of the galaxy it came from. In March 2026 comes the Jupiter encounter. 3i-ATLAS will pass within 54 million kilometers of the giant planet. NASA's Juno spacecraft will observe from Jupiter orbit. ESA's JUICE probe, if its timeline works out, might get a distant view. The observations won't be as close as the Mars flyby, but they'll provide additional data from a different viewing angle. And then, 3i-ATLAS will continue outward, past Jupiter, past Saturn, though not particularly close, out into the realm of the outer planets, growing fainter and colder with each passing month. By late 2026, it will probably be too faint for most telescopes to track. By 2027, it will be effectively unobservable. By 2030, it will have crossed Neptune's orbit and entered the region where our solar system starts to fade into interstellar space. And then it will be gone, back into the darkness, back into the cold, returning to the void it came from, carrying with it whatever changes our sun's heat induced, whatever mass it lost to sublimation, whatever cracks or fractures it developed during perihelion. But it won't be the same object that entered our solar system. It will have changed, transformed by its brief encounter with our star, transformed in ways we might understand, and in ways we might not. If 3i-ATLAS is natural, and again, all evidence suggests it is, then this transformation is purely physical. Ice to gas, solid to vapor, the inexorable process of sublimation driven by thermal energy. If 3i-ATLAS were artificial, then perhaps the transformation would be informational. Data gathered, observations recorded, samples collected, mission objectives achieved or not achieved. We'll probably never know for certain. The object will leave, our telescopes will lose track of it, and it will become just another point in space, moving on a trajectory that will take it to another star system in tens or hundreds of thousands of years. Unless something changes, unless we detect something in the coming weeks that forces us to reconsider our assumptions, unless the trajectory shifts in November, unless radio signals appear, unless the high-rise images, when finally released, show something we can't explain. These are all extremely unlikely scenarios. The probability that any of them will occur is very, very small, but that's what makes science interesting. The small probabilities, the unexpected discoveries, the moments when our models break down and we have to build new ones. 3i-ATLAS has already given us one of those moments. Not because it's artificial, but because it's different. Different from Oumuamua, different from Borisov, different from our own comets. It's taught us that we still have much to learn about how planetary systems form, how comets behave, and how the galaxy operates on scales far larger than our own neighborhood. And whether we realize it or not, it's prepared us for what comes next. Chapter 12. The Dark Forest Question. There's a question we've been dancing around. A question that makes some scientists uncomfortable. A question that feels almost inappropriate to ask in a serious scientific context. But it's been asked. It's been published in peer-reviewed preprints. It's been discussed at conferences and in media interviews. So, let's address it directly. If intelligent civilizations exist elsewhere in the galaxy, and most astronomers believe they probably do, somewhere, given the sheer number of stars and planets, then why haven't we detected them? This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked over lunch one day, "Where is everybody?" The numbers suggest we should have seen something by now. The galaxy is old about 13 billion years. Stars have been forming planets for most of that time. If life and intelligence are even moderately common, then civilizations should have arisen millions of years before us. Some of them should have developed interstellar travel. Some should have sent probes throughout the galaxy. Yet we see nothing. No radio signals, no megastructures, no obvious signs of large-scale engineering. Just silence. Many solutions to this paradox have been proposed. Maybe intelligence is extremely rare. Maybe civilizations destroy themselves before achieving interstellar travel. Maybe they're here, but hiding. Maybe they're communicating in ways we don't recognize. One of the darker solutions is called the dark forest hypothesis. It comes from a science fiction novel by Liu Cixin, but the concept is worth taking seriously. The idea is this: in a galaxy where resources are finite and civilizations' intentions are unknown, the safest strategy might be to remain silent, to hide, to avoid detection. Because if you announce your presence by broadcasting radio signals, for instance, or by building obvious structures, you make yourself a target. Other civilizations might view you as a potential threat, or as a resource to be exploited, or simply as competition for limited space and materials. In this framework, the silence we observe isn't because no one is out there. It's because everyone is hiding. Everyone is listening but not transmitting. Everyone is watching but not revealing themselves. And in the most extreme version of this hypothesis, civilizations might adopt a policy of preemptive strike. If you detect another civilization before they detect you, you might decide to destroy them before they become a threat. Not out of malice, but out of caution, out of survival instinct. This is, to be clear, speculative philosophy. We have no evidence that this is how the galaxy operates. It's one of many possible explanations for the Fermi paradox, and not necessarily the most likely. But it's relevant to 3i-ATLAS because of what Loeb and colleagues suggested in their July paper. They asked, if an advanced civilization wanted to send a reconnaissance probe to our solar system, what would that probe look like? How would it approach? What would it do? Their answer: it might look a lot like 3i-ATLAS. It would approach at high speed, making detection difficult until it was already deep in the system. It would come from a direction where background stars make early detection challenging. It would align with the ecliptic plane to facilitate close approaches to multiple planets. It would time its perihelion to occur when Earth's view is blocked by the sun, allowing for maneuvers without observation. And if such a probe were operating under dark forest principles, assuming potential hostility from whatever civilization it encountered, it would gather information while revealing nothing. No radio signals, no obvious structures, just passive observation, mimicking natural objects as much as possible. This is an interesting thought experiment. And thought experiments have value in science. They help us think through possibilities we might otherwise dismiss. But let's be clear about what this hypothesis requires. Requirement 1. Intelligent life must exist elsewhere in the galaxy. This is plausible, but unproven. Requirement 2. At least one civilization must have developed interstellar travel. This is speculative, but not impossible. Requirement 3. That civilization must have detected our solar system as a target of interest. This requires either very advanced detection methods or blind survey of many systems. Requirement 4. They must have sent a probe that arrived precisely now, during the brief window when humans are technologically capable of detecting it. This is where the probability starts to get very low. Requirement 5. The probe must be large enough and bright enough to be detected by our telescopes, yet show no signs of technology beyond what could be explained as natural. This seems like a contradiction. Requirement 6. The probe must operate under principles where passive observation is more valuable than communication or any kind of interaction. This assumes particular strategic thinking that may or may not be universal. Each of these requirements is individually questionable. Together, they form a chain of assumptions that becomes increasingly unlikely with each link. But, and this is important, unlikely is not the same as impossible. The universe is very large. Unlikely things happen. If you flip a coin enough times, you'll eventually get 100 heads in a row. The probability of any specific sequence of coin flips is microscopically small, but some sequence must occur. So while the dark forest hypothesis for 3i-ATLAS is improbable, it's worth keeping in mind as we analyze the data, not as a preferred explanation, but as a possibility to be excluded through evidence rather than assumption. The way to exclude it is through the same tests we discussed earlier: trajectory analysis, spectroscopy, radio monitoring, surface imaging. Look for anything that can't be explained by natural processes. So far, everything about 3i-ATLAS can be explained naturally. The trajectory anomalies are within expected ranges for outgassing. The chemistry, while unusual, involves compounds that can form in cometary ices. The timing, while coincidental, isn't beyond the realm of chance. The dark forest hypothesis remains a remote possibility only because we can't prove a negative. We can't prove that 3i-ATLAS is definitely natural, any more than we can prove there's definitely no invisible teapot orbiting Mars. The absence of evidence for artificial origin is not the same as evidence for natural origin, but it's close. More importantly, the dark forest framing might actually be counterproductive. If we approach every unusual object with suspicion, if we see potential threats in every anomaly, we might miss the real scientific value of studying these objects. We might waste resources chasing shadows instead of doing the careful, systematic work of characterizing interstellar material. And we might inadvertently feed public fears that are not grounded in evidence. The social media reaction to 3i-ATLAS has been instructive. Alongside the genuine scientific interest, there's been a wave of conspiracy theories, doomsday predictions, and misinterpretations of data. People claiming NASA is hiding evidence. People suggesting the object will make a surprise turn toward Earth. People linking it to ancient prophecies or secret government programs. None of this is based on reality, but it's what happens when legitimate scientific speculation gets amplified and distorted through social channels. The lesson here is that scientists have a responsibility to communicate clearly, to distinguish between what we know, what we suspect, and what we're merely considering as remote possibilities. Dr. Loeb has been criticized for not making these distinctions clearly enough. His statements about 30–40% probability of non-natural origin have been taken out of context and amplified. His "take vacations before October 29th" comment, made somewhat jokingly, has been interpreted as a genuine warning. To his credit, Loeb has also stated repeatedly that 3i-ATLAS is most likely a natural object. But those caveats often get lost in the translation from scientific papers to news articles to social media posts. This is the challenge of communicating science in an age where information travels faster than nuance. The truth about 3i-ATLAS is less dramatic than either the alien probe narrative or the "nothing to see here" dismissal. It's a genuinely interesting and unusual object that's teaching us about the diversity of the galaxy. It's worth studying carefully. It deserves our attention and our resources. But it's almost certainly not a threat, not a probe, not an invasion, just a comet. An ancient, unusual, fascinating comet from another star system. Now, let's talk about what this all means for the future. Chapter 13. What we're learning. Set aside the speculation for a moment. Set aside the alien hypothesis, the dark forest theories, the doomsday predictions. Strip away all the drama and focus on the pure science. What have we actually learned from 3i-ATLAS? Lesson 1. Interstellar objects are diverse. We cannot assume that all interstellar visitors will look like our own solar system's comets and asteroids. Each planetary system has its own formation history, its own chemical inventory, its own physical conditions. The objects ejected from these systems will reflect that diversity. 3i-ATLAS is carbon dioxide rich because it formed in conditions where carbon dioxide ice was more stable than water ice. This tells us something about the temperature and pressure in its original protoplanetary disk. It tells us about the composition of the star it orbited. It tells us about processes that occurred billions of years ago in a region of the galaxy far from our own. Lesson 2. Old objects behave differently. Most comets in our solar system are young, a few billion years old at most. They've been in stable orbits in the Kuiper belt or Oort cloud, protected from the worst of cosmic radiation and relatively unchanged since formation. 3i-ATLAS is potentially 7 to 10 billion years old. It's been wandering through interstellar space for eons, exposed to cosmic rays, bombarded by dust, experiencing temperature variations as it passed different stars at different distances. This long history has probably altered its structure. Internal fractures, layered composition, regions of different density and porosity. When such an object is suddenly heated by a sun, it might behave in ways that younger comets don't. Sudden outbursts, unusual outgassing patterns, unexpected fragmentation. Understanding these effects is important not just for interstellar objects, but for understanding the oldest objects in our own solar system, the ones that have been here since the beginning. Lesson 3. Chemistry can be exotic. The nickel without iron observation, whatever its ultimate explanation, has opened new discussions about chemical processes in cometary materials. Can nickel and iron be separated by selective sublimation? Can nickel carbonyl form naturally in space? What other compounds might exist that we haven't considered? These questions matter for astrobiology. If we're trying to understand where the building blocks of life come from, the organic molecules, the water, the minerals, we need to understand the full range of chemistry that can occur in planetary environments. Every unusual composition we discover expands that range. Lesson 4. Size distribution matters. 3i-ATLAS is large, much larger than the previous 2 interstellar objects we've detected. This raises questions about the size distribution of interstellar wanderers. Are large objects like 3i-ATLAS rare? If so, why have we found one so quickly? Are our detection methods biased toward large objects, and we're missing thousands of smaller ones? Or is the interstellar population genuinely different from what we expected? Answering these questions will help us understand planet formation throughout the galaxy. The size distribution of ejected objects reflects the size distribution of planetesimals in the original system. By studying what gets thrown out, we learn about what stayed behind. Lesson 5. Trajectories are informative. The fact that 3i-ATLAS came from the direction of the galactic core, traveling roughly parallel to the galactic plane, tells us about its ejection mechanism and travel history. It wasn't just flung out randomly. Its trajectory has been shaped by gravitational interactions over billions of years. By studying that trajectory, mapping it backward, calculating which stars it passed near, modeling the gravitational perturbations, we can piece together its journey. This is forensic astronomy. Using the evidence we can measure now to reconstruct events that occurred billions of years ago, trillions of kilometers away. Lesson 6. Coordination works. The response to 3i-ATLAS has demonstrated that the international astronomical community can coordinate effectively when presented with a time-sensitive target. Telescopes on multiple continents observed in sequence as Earth rotated. Space-based assets, Hubble, JWST, Mars orbiters were redirected to capture data. Amateur astronomers contributed observations. Data was shared rapidly through online platforms. This level of coordination will be essential in the coming years as we detect more interstellar objects. Each one offers a limited window of opportunity. We need to be able to mobilize quickly, observe efficiently, and analyze thoroughly. 3i-ATLAS has served as a test case, and we've passed. Not perfectly, there have been delays, missed opportunities, communication gaps, but overall, the global response has been remarkably effective. Lesson 7. Public interest is high. The fascination with 3i-ATLAS extends far beyond professional astronomers. Millions of people have followed its progress. Social media has been full of discussion, speculation, and debate. News outlets have covered it extensively. This level of public engagement is valuable. It creates opportunities for education. It generates support for space science. It reminds people that the universe is vast and strange and full of surprises, but it also creates responsibilities. Scientists need to communicate clearly and carefully. Speculation needs to be labeled as such. Uncertainties need to be acknowledged. The distinction between interesting and alarming needs to be maintained. We've learned or relearned that scientific communication matters as much as scientific discovery. These lessons aren't abstract. They have practical implications for how we approach future interstellar objects, how we design detection systems, how we allocate telescope time, and how we communicate with the public. 3i-ATLAS is making us better at all of these things. And that improvement will serve us well, because this is just the beginning. Chapter 14. The Future of Interstellar Astronomy. On a clear night in 2026, somewhere in Chile, the Vera C. Rubin Observatory will take its first full survey images. This telescope is revolutionary. Not because of its mirror size at 8.4 meters, it's large but not the largest. Not because of its camera, though at 3.2 billion pixels, it's the largest digital camera ever built for astronomy. What makes Rubin revolutionary is what it will do with that camera. Every 3 nights, it will photograph the entire visible sky, every object, every star, every galaxy. It will take these images, compare them to previous images, and identify anything that changed. Asteroids moving across the field, variable stars brightening or dimming, supernovae exploding in distant galaxies, and, inevitably, interstellar objects passing through our solar system. Current estimates suggest Rubin will detect somewhere between 1 and 10 interstellar objects per year, maybe more, as the survey continues and the software improves. Within a decade, we might have a catalogue of hundreds of interstellar visitors, each one unique, each one carrying chemical and physical information about another part of the galaxy. Some will be small, dark, and difficult to characterize. We'll get crude brightness curves and rough trajectory data, but not much else. Others will be large and bright enough for detailed study. Spectroscopy, polarimetry, multi-wavelength observations, maybe even radar imaging if they pass close enough. A very few, might show characteristics unusual enough to warrant the kind of intensive investigation that 3i-ATLAS has received. And maybe, someday, one of them will show characteristics that can't be explained naturally. This is the real value of building frameworks for recognizing artificial objects. Not because we expect to find them, but because we need to be prepared if we do. The search for extraterrestrial intelligence has traditionally focused on radio signals SETI, looking for deliberate transmissions from other civilizations. But interstellar objects offer another approach. If technological civilizations send probes throughout the galaxy, and if those probes pass through our solar system, we should be able to detect them. This is sometimes called artifact SETI, looking for physical evidence rather than radio signals, and it has some advantages. Radio signals decay with distance. They spread out, become diluted, eventually become indistinguishable from background noise. A powerful transmitter might only be detectable out to a few hundred light-years, but a physical object traveling through interstellar space doesn't decay. It just keeps moving. A probe launched 1 million years ago is still out there, somewhere, traveling at whatever speed it was given. If it happens to pass through our system, we can see it regardless of how long ago it was launched. Of course, the probability of any given probe passing through our specific system is vanishingly small. But if technological civilizations are common, and if they send out many probes, And if those probes travel for millions of years, then the total number of artificial objects in the galaxy might be substantial. Some calculations suggest that if even 1% of stars host civilizations that send out probes, and if each civilization sends out 1 million probes over its lifetime, then there could be billions of artificial objects wandering the galaxy. With billions of artificial objects among trillions of natural ones, the ratio is still very low, but it's not zero. And with improved detection capabilities, we might actually be able to spot them. The key is knowing what to look for. 3i-ATLAS has helped us refine those criteria. We now know that trajectory alone is not enough. Unusual alignments can happen naturally. Chemistry alone is not enough. Exotic compositions can form in exotic environments. Size alone is not enough. Large interstellar objects are rare but not impossible. Activity patterns alone are not enough. Comets can behave unpredictably. What we need is a combination of multiple factors that collectively can't be explained by any natural process. And even then, we need to be cautious. The history of astronomy is full of phenomena that seemed artificial until we understood them better. Pulsars, when first discovered, were briefly thought to be alien beacons. They're actually rapidly rotating neutron stars. Quasars were mysterious and seemed possibly artificial. They're supermassive black holes. Fast radio bursts were puzzling and unusual. They're now understood as natural astrophysical phenomena. Though the details are still being worked out, the universe is full of things that seem impossible until we figure out the physics. So, when we encounter something unusual like 3i-ATLAS, the right approach is careful investigation, not immediate conclusion. Measure everything we can measure. Consider all hypotheses, from most to least likely. Gather more data until one explanation becomes overwhelmingly more probable than the others. That's what science does. That's what distinguishes scientific thinking from speculation. And that process works. It's worked for 3i-ATLAS. Despite all the unusual characteristics, despite the speculation, despite the attention and the debate, the scientific consensus has moved steadily toward natural comet. Not because scientists are closed-minded or dismissive, but because the evidence points that way. The same process will work for future interstellar objects. Some will be boring, small, faint, unremarkable, except for their interstellar origin. Some will be interesting, unusual compositions, weird activity patterns, unexpected properties. A few might be genuinely puzzling, requiring new physics or chemistry to explain. And maybe, just maybe, one will be artificial. If that day comes, if we detect an interstellar object that shows clear evidence of technology, it will be the most important discovery in human history. It will change everything we think we know about our place in the universe. But until that day, we should approach each discovery with scientific rigor. Curiosity, yes. Openness to possibilities, absolutely. But also skepticism, careful analysis, and recognition that extraordinary claims require extraordinary evidence. 3i-ATLAS has been extraordinary enough. It's taught us about interstellar diversity, about ancient comets, about the chemistry of other star systems. It's challenged our models and forced us to think more carefully about what we expect from galactic wanderers. That's more than enough. We don't need it to be alien to be significant. Chapter 15. Tomorrow, October 29th, 2025. The day you're reading this. Somewhere right now, hidden behind the overwhelming brightness of our sun, 3i-ATLAS is experiencing the most intense heat it's felt in billions of years. The surface temperature has risen to several hundred degrees. Ice is sublimating violently. Gas is streaming away at hundreds of meters per second. Dust is being lifted off the surface and carried into space. If the object has cracks or fractures, they're expanding. If there are pockets of trapped gas, they're bursting. If the nucleus has any structural weaknesses, they're being tested to their limits. All of this is happening right now, and we can't see any of it. In 8 days, we'll know what survived. The scientific predictions are straightforward. 3i-ATLAS should emerge from perihelion intact but changed. Its coma should be larger, its tail should be more prominent. It might have developed additional jets or structures in the coma. The outgassing rate should have peaked during perihelion and will now begin to decline. The trajectory should remain consistent with gravitational motion, possibly with small perturbations from outgassing forces. The object should be heading outward from the Sun, beginning its long journey back into interstellar space. That's what the models predict. That's what the data suggests. That's what every piece of evidence points toward. And that's almost certainly what we'll observe. But there's a difference between almost certain and certain. There's a gap between prediction and observation. And in that gap lives the possibility, however remote, of surprise. What if the trajectory has changed significantly? Not just the tiny perturbations expected from outgassing, but a real deflection, a course correction. What would that mean? It would mean either intense outgassing asymmetry jets firing primarily in one direction with enough force to measurably alter the orbit. This can happen naturally. Comets have been observed to undergo non-gravitational acceleration, or it would mean something else, something that would require us to reconsider our assumptions about what we're observing. What if the object has fragmented? Not just minor shedding of dust and small particles, but major breakup into multiple distinct pieces. It would mean the nucleus was more fragile than its size suggested. Perhaps honeycomb structure, perhaps deep fractures that opened under thermal stress. This has happened to other comets. It's not evidence of anything beyond natural structural weakness. But if the fragmentation pattern is unusual, if the pieces separate in unexpected ways, or if some pieces show different activity levels than others, that would be interesting. Worth investigating carefully. What if the high-rise images, when released, show surface features that don't look like what we expect from a comet? They probably won't. The resolution won't be high enough to see small details. And even if there are geometric patterns, they could be explained by natural processes, crystal structures, erosion patterns, impact craters. But could be explained and are explained are different things. If we see something genuinely anomalous, we'll need to investigate further. These are the questions we'll be asking in November. These are the observations we'll be making. These are the tests that will either confirm 3i-ATLAS as a natural object beyond any reasonable doubt, or in the extremely unlikely case, raise new questions. The scientific process doesn't end with perihelion. It continues through the reappearance, through the December observations, through the Jupiter flyby, and on until the object becomes too faint to track. Each observation adds data. Each data point constrains the possibilities. Each constraint makes some hypotheses more likely and others less likely. That's how we learn. Not through dramatic revelations, but through patient accumulation of evidence. Not through leaps of imagination, but through careful testing of ideas against reality. Whatever happens over the next few weeks, 3i-ATLAS has already earned its place in astronomical history. It's the third confirmed interstellar visitor, the largest and fastest we've detected, the first to show such extreme carbon dioxide dominance, the first to be observed by spacecraft around Mars during close approach. These achievements don't require it to be artificial. They don't require conspiracy or cover-up. They don't require anything beyond what it obviously is. A remarkable chunk of ancient ice and rock from another star system, caught briefly in our telescopes before returning to the cosmic ocean. But that's enough. That's more than enough, because 3i-ATLAS is teaching us that the galaxy is stranger and more diverse than we imagined. That our solar system isn't the template for all planetary systems. That objects billions of years old can still surprise us with their behavior. It's teaching us humility that we don't know everything, that our models are incomplete, that nature has more variations than our theories encompass. And it's teaching us wonder that out there, beyond our sun's sphere of influence, in the vast dark between stars, countless objects are drifting. Some have been traveling for longer than our planet has existed. Some carry materials from the early universe. Some might be more than they appear. Tomorrow, 3i-ATLAS reaches perihelion, the moment of maximum intensity, the peak of its interaction with our Sunday, and we wait, in the darkness, on the wrong side of our star, unable to observe, unable to measure, unable to know. In 8 days, we'll see it again, and we'll learn whether it passed through perihelion unchanged or whether something happened during those hidden hours that we didn't predict. The probability is that nothing unusual occurred, that the object followed the laws of physics exactly as expected, that it's now beginning its long, slow fade back into the darkness from which it came. But probability isn't certainty. And the gap between them, that small space where unlikely things become real, is where discoveries happen. So we wait. We watch. We prepare our telescopes and our instruments and our questions. And on November 7th, when 3i-ATLAS emerges from behind the sun, we'll point every sensor we have at that patch of sky and look, looking for answers, looking for confirmation, looking for the expected, but also always looking for the unexpected, for the anomaly, for the thing that doesn't fit, because that's how science progresses, not by confirming what we already believe, but by finding the exceptions, the outliers, the things that force us to think harder and look deeper. 3i-ATLAS might be one of those things, or it might not. Either way, it's been worth watching, worth studying, worth the time and resources we've devoted to understanding it. And whatever we learn over the next few weeks will prepare us for the next visitor, and the one after that, and all the hundreds that will follow in the years ahead. The age of interstellar astronomy has begun. We're learning to read messages written in ice and stone and chemistry, messages that have traveled across light years to reach us. 3i-ATLAS is one message, one story, one glimpse into the vast library of the galaxy. We're fortunate to be alive at the moment when we can finally start reading. Chapter 16, The Black Swan. The story of 3i-ATLAS is not just a story of astronomical observation. It is a story of a deep and public schism, a divide between the comfortable consensus and a few prominent voices asking a deeply uncomfortable question. At the center of this storm is Dr. Avi Loeb, an astrophysicist from Harvard University. To the scientific establishment, 3i-ATLAS is a fascinating natural comet. To Avi Loeb, it is something far more. He has warned, publicly, that this object could be a black swan event, a term for a high-impact event that is so rare it is impossible to forecast under normal circumstances, an event that, in hindsight, appears to have been inevitable. An event, he says, that could have major implications for humanity. Loeb is not speaking in quiet whispers. He is on television, he is writing articles, he is forcing the world to look at what he sees. And what he sees is a Trojan horse, an object that masquerades as a natural comet, but is, in fact, something else, something technological. To illustrate the danger, he uses a stark analogy. We are on a blind date with this object. You often assume that the dating partner would be very friendly, Loeb explains. But you have to worry about serial killers as well. This is not a position born from fantasy. It is a conclusion drawn from a list of anomalies, a list of things about 3i-ATLAS that simply do not add up. The first anomaly, its sheer size. 3i-ATLAS is estimated to be Manhattan gent-sized. Based on data from the Webb telescope, Loeb infers the object could weigh an astonishing 33 billion tons. This makes it, by his calculation, at least 1,000 times more massive than the previous interstellar objects we have seen, Oumuamua and Borisov. The discovery of this object, this giant, presents a profound statistical problem, a problem Loeb poses as a question. And the question is, he declares, why is such a giant object delivered to our inner solar system when we saw only small ones before? If interstellar objects are common, we should have detected millions of small ones before ever seeing a giant like this. The fact that we found this first is suspicious. The second anomaly, its trajectory. As we know, 3i-ATLAS is not just falling in from a random direction. It is moving in almost perfect alignment with the ecliptic plane, the flat disk where all the planets orbit. The random chance of this is less than 0.2%, but it's more than just the alignment. The path itself seems curated. Loeb and his colleagues published a paper analyzing this path. They found the trajectory brings 3i-ATLAS surprisingly close to Venus, Mars, and Jupiter. The cumulative probability of an object having this specific alignment and these precise planetary flybys, less than 0.005%. This is not just rare. It is an alignment that an intelligent probe might choose for reconnaissance. In another paper, Loeb and his colleagues explore this idea explicitly. The hypothesis that 3i-ATLAS is a technological artifact, and this leads to the third and most alarming anomaly: the timing. The object is now just days away from making its closest approach to the Sunday, and it is at this exact moment, the moment of peak velocity, peak energy, and peak activity, that 3i-ATLAS will slip behind the Sun, completely hidden from our view. To Avi Loeb, this is not a coincidence. This is an opportunity for a maneuver. Chapter 17, The Mothership Maneuver, October 29th, perihelion. For a comet, it is the moment of greatest trial, a baptism by fire. For a spacecraft, it is the moment of greatest potential. In orbital mechanics, it is the home of the Oberth effect. It is a principle that spacecraft use to gain speed. Firing an engine when moving at your absolute fastest, at your closest point to a massive body like the Sun, gives you the biggest possible boost in energy. Loeb and others have proposed that 3i-ATLAS might be here to do the opposite, a reverse solar Oberth maneuver, a high-thrust braking strategy. To use the Sun's immense gravity and radiation not to accelerate, but to slow down, to change its path, to stop being a visitor, and to stay. And the object will be perfectly hidden by the Sun's glare when it does it. This is the mothership hypothesis. The theory that 3i-ATLAS is not a passive ball of ice, but a massive, active, intelligent craft. And if it is a mothership, this is the moment it might release its payload. The more likely scenario, Loeb has suggested, involves a mothership that releases mini-probes which perform a reverse Oberth maneuver to slow down at perihelion. Probes that could, he calculates, intercept Earth. This idea has captured the public imagination. And it's not just Loeb. Physicist Dr. Michio Kaku, a professor at the City College of New York, has said that the astronomical community is sharply divided. The majority believe it's just another rock from deep space, Kaku said. But a growing number suspect it may be something more, perhaps an intelligent visitor. Kaku frames October 29th as a test. The day we find out, he argues that as 3i-ATLAS whips around the Sun, we will see if its motion obeys the known laws of physics. If it gains more energy than expected, more than gravity alone can provide, that would be the proof. That would mean, Kaku states, in no uncertain terms, that some intelligence is guiding it. It would be, as he puts it, a cosmic calling card. This is the very heart of the alien probe theory. It recontextualizes everything we've seen so far. That strange sunward jet we observed back in July and August, the one that pointed toward the Sun, to the consensus, it's a standard cometary feature. To Loeb and his colleague, Adam Hibbard, it was something else entirely. If the object is an alien spacecraft slowing down, Loeb wrote, and the anti-tail is breaking thrust, then this change would be entirely expected. And the fact that the jet disappeared in September, that wasn't the solar wind overpowering it. That was the engine shutting down. The braking burn was complete, right on schedule, just before the final maneuver behind the Sunday. This is the narrative. A massive, intelligent, technologically advanced object is using our Sun as a gravitational tool, and it is doing so in secret, hidden behind the glare. It is a terrifying, cinematic idea, and for those who believe it, there is one piece of physical evidence that stands above all else. A single chemical signature so strange, so out of place, that it has no known natural precedent. A compound that should not be there. Chapter 18. Exhibit A. The industrial alloy. Let's return to the chemistry problem. We knew from the start that 3i-ATLAS was strange, the dominance of CO2, the sudden, fire hose-like blast of water. But the real mystery was the metal. In September, astronomers detected nickel vapor in the coma. This was odd, but not impossible. What was impossible was what was missing. There was no detectable iron. In every comet ever studied from our solar system or beyond, nickel and iron appear together. They are cosmic brothers, forged in the same stellar cores and blasted across the galaxy in the same supernovae. They are always found in comparable amounts, but not in 3i-ATLAS. This object was emitting a plume containing 4 grams of nickel per second, with no iron. This discovery was so bizarre that scientists scrambled for an explanation. The leading natural theory was that carbon monoxide in the coma was reacting with nickel from dust grains to form a new exotic compound. That compound has a name: nickel tetracarbonyl, a toxic, volatile, organometallic gas. And this is the smoking gun for the artificial hypothesis. Because according to Avi Loeb, this metal alloy has never before been witnessed in nature. There is only one place, Loeb told the Post, where that is known to exist, and that is in industrially produced nickel alloys. He is correct. On Earth, nickel tetracarbonyl is not a natural substance. It is a key part of the MON process, an industrial technique used to refine and purify nickel metal. It's used to create high-strength metal coatings, including for the aerospace industry. It is, by every definition we have, a human-manufactured compound. This was never observed for any other object, Loeb states. This was a process that we can imagine only because it was used in industry. The implications are staggering. We are observing an object the size of a city that is venting a compound previously known only from industrial manufacturing. This, combined with the lack of a tail, the sunward-pointing jet, the statistically impossible orbit, and the clandestine perihelion timing. The case for alien probe seems to be growing stronger. It is a terrifying, compelling, and revolutionary idea, and, according to the vast majority of the world's scientific community, it is almost certainly, completely, and demonstrably wrong. Chapter 19. The Case for Nature. The artificial hypothesis is a good story. It's a fantastic story. But the job of science is not to tell the best story. It is to find the truth, and the truth, according to the overwhelming scientific consensus, is that 3i-ATLAS is not a spaceship. It is a comet. A visitor, yes. An ancient traveler, absolutely. From a star system very different from our own. But it is a natural object. The European Space Agency, or ESA, has been direct. Dr. Michael Kuppers, an ESA scientist, stated plainly, 3i-ATLAS looks like a comet and it behaves like a comet. NASA's lead scientist for solar system small bodies, Tom Statler, has been just as clear. It looks like a comet. It does comet things, Statler said. It very, very strongly resembles, in just about every way, the comets that we know. He acknowledges its peculiarities. It has some interesting properties that are a little bit different from our solar system comets, but it behaves like a comet. And so, he concludes, the evidence is overwhelmingly pointing to this object being a natural body. It's a comet. The case for nature is not a dismissal. It is a systematic, scientific takedown of every anomaly on Loeb's list. Let's start with the braking thruster. That supposedly artificial, sunward-pointing jet. It turns out, this is not an anomaly at all. It is standard cometary anatomy. On August 2nd, new images were captured by the 2-meter twin telescope at Spain's Teide Observatory. These images, a composite of 159 separate exposures, provided the definitive, natural explanation. The jet is not a thruster. It is a geyser. Miquel Serra-Ricart, an astrophysicist at the observatory, explained the process. Comets do not heat evenly. The side facing the sun warms up the fastest. If a particular weak spot on the surface, a patch of frozen volatile ice, gets hot enough, the supply of sublimated gas beneath it will blast out like a geyser. And because this geyser is erupting from the sun-facing side, the jet of dust and gas shoots toward the sun. As the comet's nucleus rotates, this jet sprays out, creating the fan-shaped appearance seen in the images. This isn't new. This isn't theoretical. The exact same behavior was seen in the famous comet Neowise back in 2020. So, what about the jet shutting down in September? The engine powering off? That, too, has a perfectly natural explanation. As 3i-ATLAS got closer to the sun, the solar wind, the constant stream of particles from our star, grew stronger. The real cometary tail, the one that always points away from the sun, began to form. This anti-solar tail grew brighter, fanned out, and simply overwhelmed the fainter, sunward-pointing jet. The anti-tail didn't shut down. It was obscured by the normal tail. The physics are predictable. The behavior is natural. Finally, there is the industrial alloy, the nickel tetracarbonyl, the smoking gun. Even here, the scientific consensus holds. Yes, it is strange, but strange does not mean artificial. The authors of the Keck study itself, the very people who found the nickel, suggested natural, though exotic, chemical processes. Other scientists propose that in the unique, cold, C2-rich environment of the comet's coma, exotic reactions are occurring, reactions that can, in fact, form this compound naturally. This isn't an industrial process, it's a cosmic one we have simply never been in a position to witness before. This object is from another star. It may be billions of years older than our Sunday. It formed in a place with different chemistry, different materials, and different rules. Why would we ever expect it to perfectly match the comets from our own backyard? The consensus is clear. The case for nature is built on observation, physics, and chemistry. There is no alien probe. There is no mothership. But in science, consensus is not proof. To settle the debate, we need more. We need to see the object up close. We need the data. Chapter 20. The data we have and the data we don't. On October 3rd, 2025, humanity got its first close-up look at 3i-ATLAS. The object passed within 30 million kilometers of Mars, and we were waiting for it. An entire fleet of robotic explorers, orbiters from Europe and America, were ready. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter, TGO, turned their eyes away from the red planet and toward the interstellar visitor. The challenge was immense. These cameras are designed to photograph the bright, sunlit surface of Mars. Just a few hundred kilometers below them, 3i-ATLAS was 30 million kilometers away, and 10,000 to 100,000 times fainter. And yet, they saw it. The first images were released. The world held its breath and saw a fuzzy, white dot. In an animated sequence from the TGO orbiter, 3i-ATLAS appears as a faint, slightly extended blob, drifting steadily downward against a backdrop of black space and pinpoint stars. There was no mothership, no engines, no lights, no structure. It was exactly what ESA said it would be. A relatively small comet 30 million kilometers away. The images captured its coma, the halo of gas and dust surrounding the nucleus. It looked like a comet. We even got a view from the surface. NASA's Perseverance rover, parked in Jezero crater, pointed its Mastcam Z camera to the Martian sky. The resulting images were faint. Too faint to see anything clearly. But astrophotographer Simeon Schmaus had an idea. He downloaded 20 of the raw images, stacked them on top of each other, and processed them. And there, right where the comet was predicted to be, he found it, a faint smudge of light. A super faint smudge. The view from the surface of Mars confirmed the view from orbit. This was a massive blow to the artificial hypothesis. The closest ever images of the object showed nothing artificial, but the debate was not over, because there was one set of images the public still had not seen, the most important ones. NASA's Mars Reconnaissance Orbiter, MRO, This spacecraft carries the high-resolution champion of the solar system, the HiRISE camera. HiRISE is the most powerful telescope ever sent to another planet. It was designed to resolve fine details on the Martian surface. Pointed at 3i-ATLAS, it should have captured the sharpest, clearest, most detailed images of the object yet obtained. These are the images that could settle the debate. The images that could show, once and for all, if there is a solid, technological object inside that fuzzy coma. But as of today, October 28th, those images have not been released. The reason, according to NASA, is painfully mundane. A U.S. government shutdown. Non-essential government functions are paused. NASA's communications departments are furloughed. The data pipeline is clogged. This procedural delay, at this critical moment, has become a vacuum. And into that vacuum, speculation and conspiracy have rushed. Online forums are ablaze with claims of a cover-up, that NASA has the images, and they show something the public isn't supposed to see. The delay is feeding the very narrative the scientific consensus is trying to fight. Dr. Loeb himself has publicly voiced his impatience. "Who cares about the communication departments?" he stated, frustrated. "We want to see the data from the scientists." The ESA images show a fuzzy dot. The rover images show a faint smudge. The world is now waiting for HiRISE. Chapter 21, The Global Campaign. While the public debate rages, fueled by missing data and Trojan horse theories, the world's official scientific organizations are not waiting. They are mobilizing. The International Asteroid Warning Network, or IAWN, has launched an unprecedented, large-scale global campaign. This is the very first time in history that scientists have coordinated a structured, international observation of an interstellar visitor. The launch of this campaign has itself been twisted by conspiracy theories, cited as proof that NASA has quietly activated its planetary defense network. But the truth is public, and it is far less alarming. IAWN's own website clarifies the mission. This is not a planetary defense alert. This is an observing exercise. NASA, ESA, and IAWN have been unanimous and explicit. 3i-ATLAS poses no physical threat to Earth. It is not on a collision course. Its closest approach to our planet will be on December 19th, 2025. It will pass us at a safe distance of 270 million kilometers. That is over 1.7 times the distance between the Earth and the Sunday. This is not an emergency. IAWN states this is a great opportunity, a chance to test our global networks, to improve our tracking methods for fast-moving objects, to rehearse how scientists respond when unfamiliar objects approach, and above all, it is a chance to study this rare time capsule from another star. Professional and amateur astronomers alike are being trained in advanced methods for data collection. Every telescope that can be pointed at 3i-ATLAS will be. But the most exciting data won't come from Earth at all. Right now, 2 spacecraft are hurtling through the solar system on their own missions. ESA's Hera probe and NASA's Europa Clipper. By a stroke of cosmic luck, their trajectories are about to line up perfectly. It is a rare and fortuitous alignment. Between late October and early November, both spacecraft are predicted to fly directly through the tail of 3i-ATLAS. Not the visible dust tail, but the invisible ion tail, a vast stream of charged particles. Their particle sensors are designed to sample the space environment, and they will, for the first time, directly sample the material from an interstellar object. We have virtually no data on the interior of interstellar comets, said Samuel Grant, who led the research on the alignment. Sampling the tail in this way is the closest we can currently get to a different part of the galaxy. We are finally going to touch this messenger from another star system. But even this opportunity hangs by a thread. The U.S. government shutdown. Europa Clipper is in cruise mode. Not all of its instruments are activated. The alignment window is between October 30th and November 6th. If the shutdown is not resolved, if the command cannot be sent to awaken the instruments, we may miss this chance completely. While we wait, other eyes are turning. ESA's Jupiter Icy Moons Explorer, JUICE, will observe the comet in November, just as it emerges from behind the Sun at its peak of activity. And in March 2026, as 3i-ATLAS sails past Jupiter, NASA's Juno probe will get one last look. The debate rages. The world is watching. The natural comet versus the alien probe. The mundane explanation versus the black swan event. But the time for pure speculation is ending. The data is coming. Epilogue. What we know. Let's end where we began. With what we actually know. With facts instead of speculation. With observation instead of interpretation. 3i-ATLAS is an interstellar object, confirmed by its hyperbolic trajectory and high velocity relative to the Sunday. It was discovered on July 1st, 2025, by the ATLAS telescope network in Chile. It measures approximately 5 to 6 kilometers in diameter, possibly larger, making it the largest interstellar object yet detected. It is composed primarily of carbon dioxide ice, with water ice and various other volatiles in smaller quantities. It has been observed to emit nickel vapor, initially without detectable iron, though iron emissions appeared later in its approach. It displayed a sunward-pointing jet in July and August 2025, which transformed into a more conventional antisolar tail by September. It passed within 29 million kilometers of Mars on October 3, 2025, allowing spacecraft around Mars to capture the closest images yet obtained of an interstellar object. It reaches perihelion today, October 29, 2025, at approximately 1.36 AU from the Sun, hidden from Earth's view by solar glare. It poses no threat to Earth, coming no closer than 1.8 AU, approximately 270 million kilometers, in December 2025. Its trajectory is consistent with pure gravitational motion, with no confirmed evidence of non-gravitational acceleration. It is almost certainly a natural comet from another star system, displaying unusual but explicable properties based on its exotic formation environment and ancient age. These are the facts. Everything else, the speculation about artificial origin, the dark forest theories, the implications for galactic civilizations, is hypothesis. Interesting hypothesis, worth discussing, but not supported by current evidence. Science works by testing hypotheses against observations. So far, the natural comet hypothesis explains all observations adequately. The artificial probe hypothesis requires additional assumptions that aren't supported by data. That could change. New observations might reveal something we haven't seen yet. But until they do, the most scientific position is to accept the most parsimonious explanation. 3i-ATLAS is a comet, an unusual comet, a fascinating comet, a comet that's teaching us things we didn't know about planetary systems and interstellar chemistry. But a comet nonetheless, and that's wonderful. We don't need alien artifacts to make the universe interesting. The natural universe is strange enough, diverse enough, surprising enough to keep us occupied for centuries. 3i-ATLAS is a reminder of that. A visitor from the cosmic depths, carrying within it the chemical history of another world. An ancient traveler, older than our civilization, older than our species, older than most life on Earth. It passed through our solar system for a few brief months. We pointed our telescopes at it. We gathered data. We learned what we could learn. And now it's leaving. Back into the darkness. Back into the cold immensity of interstellar space, carrying with it whatever changes our sun induced, whatever mass it lost, whatever transformations occurred during its brief encounter with heat and light. We'll never see it again. In a few years, it will be too far and too faint for any telescope to detect. In a few decades, it will have left the gravitational influence of our sun entirely. In a few millennia, it will be approaching another star system, where perhaps another civilization will point their instruments at the sky and wonder what this ancient visitor might tell them about the galaxy. That's the story of 3i-ATLAS, not the story of an alien invasion or a black swan event or a dark forest probe, just the story of a comet, a traveler, a messenger from elsewhere, briefly visible, soon gone. But while it was here, we watched, we learned, we marveled, and that's enough, more than enough. That's everything we could ask for from the universe. The opportunity to see something we've never seen before, to measure it, to understand it, and to be reminded that there's always more to discover. 3i-ATLAS has given us that opportunity. And for that, we should be grateful. This documentary was compiled from verified astronomical observations, peer-reviewed scientific papers, official statements from NASA and ESA, and public data releases as of the 28th of October 2025. All scientific claims presented have been sourced from published research or direct observations. Speculative hypotheses have been clearly labeled as such and distinguished from confirmed observations. The trajectory data, chemical analyses, and physical measurements discussed represent our best current understanding based on available evidence. As with all active areas of scientific research, these conclusions may be refined or revised as new data becomes available. For those interested in following the continued observation of 3i-ATLAS, updated astrometric data is available through the Minor Planet Center. Spectroscopic results are being published in astronomical journals as they're processed, and imaging from various telescopes continues to be released through official space agency channels. The question of whether we are alone in the universe remains one of the most profound mysteries humanity faces. Objects like 3i-ATLAS remind us that the answer, whatever it may be, lies not in speculation or assumption, but in careful observation, rigorous analysis, and the patient accumulation of evidence. The cosmos reveals its secrets slowly, to those willing to watch and wait and wonder. This is the scientific method at work. This is how we learn. This is how we grow our understanding of the universe, one observation at a time. And somewhere out there, beyond the reach of our telescopes, in the darkness between stars, other visitors are traveling, other time capsules from other worlds, other messages waiting to be read. We have learned to recognize them. We have learned to study them. We have learned to ask the right questions. Now we wait for the answers. Disclaimer: this documentary presents the scientific understanding of 3i-ATLAS as of the 28th of October 2025. The object is still under active study. Some interpretations presented, particularly regarding the artificial origin hypothesis, represent minority scientific viewpoints and should be understood as speculative rather than consensus positions. The overwhelming scientific evidence supports a natural cometary origin. This presentation has attempted to distinguish clearly between confirmed observations, probable interpretations, and speculative possibilities throughout.